Welcome back, guys. Today we're going to be looking at the second derivative test, which in many ways is going to be a continuation of what we looked at in our last lesson, where we were looking at concavity or concavity. And so before we get into what the actual second derivative test is, let's look at what we know already. So we have a graph here, and it's opening upward. And so based on our last lesson here, we know that this is concave up. And if it's concave up, then we know that the second derivative has to be greater than 0, or it has to be positive. And so at our point here, this would be our critical point. We can also think about what's happening with the first derivative. Well, with the first derivative, this part of the graph is decreasing, and then this part is increasing. And right here, we have the first derivative equaling 0. So if the first derivative is equal to 0, and the second derivative is positive, then f has a local minimum at x equals c. So that's the first part of our second derivative test. So if our first derivative is 0 and our second derivative is positive, then the function has a local minimum. Now, earlier on, we were looking at first derivatives. We were looking at that in a previous unit as well as this unit. If the first derivative is equal to 0, that just means that we possibly have. There is a possible max or min. There's no guarantee of that. The second derivative test is going to be what confirms that. So if the first derivative at a critical point is 0, then there are possible maxes or mins. So to determine if there's an actual max or min, we have to look at the critical points and then sub into the second derivative. So to determine if there are maxes or mins, max or mins at that critical point, then we have to sub into f double prime of x. Or we could use a number line. Or we could use a number line or an interval chart. So all of those could be used. But ultimately, we still have to be testing that second derivative to confirm that there's a local max or min. If you want a little diagram to kind of help remember this, you might think if the first derivative is 0 and the second derivative is positive, then we have a minimum. Okay, so it's opening up. And so then if we look at the second case here, similar, now we're looking at concave down. So if the graph is concave down, then we know that the second derivative is negative. We also know that we are going from increasing to decreasing. And we know right here our first derivative is 0. So if the first derivative is 0 and the second derivative is negative, then we have a local maximum at that point. And again, we can sub in or we can use a number line or an interval chart. So again, if you wanted a little diagram to help remember that, if the first derivative is 0 and the second derivative is negative, then we have a local maximum. Now, some other things to know. The critical values for the second derivative, i.e. when the second derivative is equal to 0 or the second derivative does not exist, are sometimes difficult to interpret, or we can describe them as inconclusive. And when that happens, we have to go back to the first derivative. So if there is a second derivative equaling to 0, that means there could be a change in concavity. There could be a local max or min. There could be a point of inflection, but we don't know necessarily. So that's where we have to go back to the first derivative test. Now, if I were to give you some information here, if I were to tell you that, I'm just going to give you a random function here, f of 8 equals 5. So the value of the function when x is 8 is 5. The value of the derivative at 8 is 0. And the second derivative at 8 is negative 4. If I give you that information, I want you to ask yourself, can you get a visual of some of what's happening with that graph? Well, the first part is just a point on the graph. Okay. The first derivative, if f prime of 8 equals 0, then all that tells us is there may be a point max or min. So there may be. But we don't know for sure. Okay, so there may be a max or min, a local max or min, but so there may be a local max or min, but it's not until we look at the second derivative that we know for sure. Now, in this case, the second derivative is negative, so that means we have f double prime of that constant being less than 0. That means it's concave down, and that means we have a local maximum. So again, first derivative tells us whether there may or may not be a max or min. The second derivative is what confirms that yes, there's a max or yes, there's a min. All right, so let's take a look at some examples here. So the first question says to find, or asks us to find the local maximums or minimums of the following functions using two methods. So our first method is going to be the first derivative test. All right, so we take our first derivative, f prime of x gives us 6x minus 6x squared. We set that equal to 0. We're factoring, we've got 6x times 1 minus x. So our critical values are 0 and 1. And so then we can set up our interval chart. We can set up a number line. If we do this one as a number line, we've got a point at 0. We've got a point at 1. And this is for f prime of x. And so you can sub in some test points. And as you do that, you will find out that this part here is negative, this part here is positive, and this part here is negative. And so what that tells us is that this part of the graph is going from decreasing to increasing, and this one is going from increasing to decreasing. So we have a local min at 0, and we have a local maximum at 1. And if we sub those in to our original function, we can get our points. So the local min at 0, 1, and our local max at 1, 2. All right, now if we try the other method here using the second derivative, we have method 2 using the second derivative test. So we take our second derivative, we've got f double prime of x equals 6 minus 12x. Now we have our critical points from doing the first derivative, and when we sub those in, we're going to check to see if it's positive or negative. So f double prime of our first critical point is 0, is 6 minus 12 times 0. Now it's not so important that you know what that value is, but whether you know it's positive or negative. So we've got 6 minus 0. 6 minus 0 is a positive value. So that means we have a local minimum because it's positive. If we sub in f double prime of 1, 6 minus 12 times 1, 6 minus 12 is negative. That means we have a local max. And so we're going to have, similar to before, a local min at, again, we'd sub into our original function to get the y value, and a local maximum at 1, 2. Now, if we wanted to get a visual of what that graph might look like, we can sketch a quick Cartesian plane here. We know that we have a critical value at 0, and we know that we have in here. So we have a local minimum happening at 0, 1. So that's right here. We know we have a local maximum happening at 1, 2. And that's all we really know without finding all of our intercepts. But we know that it's going to look something like that. Right. And so that's not necessarily an x-intercept. That's just where it's just where it's crossing the graph. I didn't have a mark specifically marked there. But we know there from that information where our local max and our local min are. All right, so let's take a look at another example here. So we have g of x equals x cubed. Well, we start off with g prime. So g prime of x is 3x squared. And if we find our critical values there, set that equal to 0, divide by 3, and then square root, we're going to have x equals 0. And so we could, again, check a number line or do an interval chart. Okay, so this time I'll maybe do it as an interval chart. So from negative infinity to 0 and 0 to infinity. This part here I can use a test point maybe of -5. -5 squared. -5 squared is 25 times 3. This will be positive. And this part will also be positive. So it's increasing and it's increasing. If I was to look at that on a number line, my graph is increasing and increasing. So this would tell me that there is no max or min. But we still have to check to see if there is any other points of inflection. So we're going to take the second derivative. Second derivative of x is 6x. So we're going to sub in our critical point. G double prime of 0 is 6 times 0, which is 0. So we have no max or min. We have no max or min. That's what we have from our first derivative test. Let's check with an interval chart here. So we've got an interval chart, and we're going to plug in the 6x, going from negative infinity to 0 and infinity to 0. Subbing in, again, test, I can use the same test value. So -5, this would give me a negative value. This would give you a positive value. So this tells me there is a change in concavity. So while there's no max or min, there is a change in concavity. So that tells me that I have a point of inflection. So there's no max or min, but a point of inflection at x equals 0. And again, if we sub in, that would happen at 0, 0. So again, trying to visualize this graph, our critical point is happening right at 0. We're going from increasing to increasing. So it's going to look something like that. All right, let's continue on to some examples here. The next one, it says, asks us to use the second derivative test to find any maximums or minimums. So we're not going to focus on the first derivative so much. We're just going to go into the second derivative. But again, we have to use the first derivative to find our second derivative. So first derivative here, we have, I'm going to rewrite this to begin with. We got h of x equals x squared plus 16 times x to the -1. So h prime of x is 2x minus 16 x to the -2. So 0 equals 2x minus 16 x to the -2. Now we can certainly just bring the 2x over and solve, but we will end up losing that one of our values is x. So we could rewrite this. If you choose to, we could write it as 2x equals 16 over x squared and then solve. But you have to remember then your NPV, you would have an NPV of x. Another way to look at this is 0 equals 2x. We can pull out 2x to the -2, and that's 1. So x cubed minus 8. And then we could solve this. So we'd end up with the same as having 2 times x cubed minus 8 all over x squared. Again, we would still end up getting our same answers, and we would still have to consider that x is an NPV. So our x values are going to equal 0 and 2. Now, because this is a vertical asymptote, we don't need to check it. And it's a vertical asymptote because it's one of our NPVs. So we don't have to sub this one into our second derivative test because we already know it's a vertical asymptote. So let's get our second derivative here. We've got 2 plus 32 times x to the -3. we're going to sub in that critical point to see if it's positive or negative. So 2 plus 32 times 2 to the negative 3. And again, it does not matter whether or what the actual final answer is. We just care about whether it's positive or negative. In this case, it equals 6, meaning it's positive, meaning we have a local minimum. And so it's a local minimum at f of 2, which equals 12, or we could write that as 2 comma 12. So it's a local minimum at 2 comma 12. Okay, we're going to continue on just with a couple more examples today. Next question here we have y equals 2x cubed minus 3x squared minus 12x plus 18. So we take our first derivative, 6x squared minus 6x minus 12. Set it equal to 0 to find our critical points. So we've got 6 brackets, I'm factoring out a 6, minus x minus 2. And continue to factor, x minus 2, x plus 1. So our critical values are x equals 2 and x equals number 1, or negative 1. We'll take our second derivative, and that gives us 12x minus 6. So when x equals 2, we would have y double prime equaling 12 times 2 minus 6, which is a positive value. Positive value means it's a local minimum. Think about a smiley face. And when x equals negative 1, y double prime equals 12 times negative 1 minus 6 equals a negative, meaning we have a local maximum. So our final answer here, we have a local minimum at 2 comma negative 2. Again, you'll get those by subbing them into your original equation or original function. And local maximum at negative 1 comma 25. All right, one final example here. We're actually going to go through quite a bit here. We're going to actually go through what we've learned today and then start to graph the actual function. So find the maximum and minimum values of y equals x to the 4th minus 8x cubed. And then we're going to use those together with concavity and points of inflection and intercepts to sketch the actual curve. All right. So if you're making notes on this, it's probably going to take about a full page to fill all of this in. So we're going to start off with our first derivative. So y prime equals 4x cubed minus 24x squared. Y double prime, so if we take the second derivative, we're going to have 12x squared minus 48x. Now you can factor that if you wanted to, and just like we can factor the first derivative, it might come in handy to have that factored for when we're finding our critical points later. Same thing here, if we wanted to factor this out, we would have 4x squared times x minus 6. So that factoring piece you can do now, or you can do it later. So the first thing we're going to do is we're going to look for our critical points. And our critical points happen when the first derivative is equal to 0. And so we've already factored it from above. So 4x squared times x minus 6. Our critical points happen at x equals 0 and x equals 6. Now we're going to use the second derivative to determine if we have any maxes or mins. So this is where we're looking at the second derivative of our critical points. So second derivative of 0, 12 times 0 squared minus 48 times 0 gives us 0. So this is inconclusive. We don't know if that means it's a max or a min or a point of inflection yet. So at this point, this is inconclusive. So let's check the second point. So second derivative of 6 we've got 12 times 6 times 6 minus 4. So I've used the factored form there. That would give me 144, meaning it's positive. And if it's positive, that means we have a local min or a local minimum. Okay. And I'm saving a little bit of the work here, but our local minimum happens at 6, negative 432. So I've done some of that legwork. You would have to go and actually plug those in to the equation to get that second point. So local minimum at 6, negative 432. So we know that so far. All right. Now, because that first one is inconclusive, the second derivative equaling 0 is inconclusive, we have to go back to our first derivative. So if the second derivative is equal to 0, then we go back to the first derivative. The first derivative test. Okay. And again, you can use this as a number line. You can do this as an interval chart. For this one here, I'm going to choose to do a number line. We've got a critical point at 0. We've got a critical point at 6. And this is for our first derivative. So our intervals are going from negative infinity to 0, 0 to 6, and 6 to infinity. And so we're going to sub in test values. And as we do that, we're going to find out that this part of the graph is decreasing, this part of the function is decreasing, and this part of the function is increasing. So what does that tell us? Well, if the first derivative is negative on both sides of 0, that means there's no max or min. So it's going down here and it's going down here. So if the first derivative is negative on both sides of 0, there is no max or min at that point. All right, so let's go into checking our concavity. All right, so for concavity, we're looking at our critical points with regards to the second derivative. So concavity, we're looking at our second derivative again. Remember, second derivative in its factored form was 12x times x minus 4. So that means our critical values are happening at 0 and 4. So again, you could use a number line or you can use a chart. I'll show you the interval chart here. So our interval chart, we've got 12x, we've got x minus 4, and then we're looking at how that actually affects the second derivative. So first interval is negative infinity to 0, and then we've got 0 to 4, and we've got 4 to infinity. So we have negative, negative, and positive, positive, and negative, making it negative again. You would be using test points. When I did my test points here, I chose to use test points of negative 4, and a test point of 2, and a test point of 5. So again, you're just choosing any test points that fit within those intervals. And for the last one here, we would have positive, positive, and positive. So again, if it helps to visualize as a number line, you can certainly do that. So 0 and 4, we're going from positive to negative. That means it's concave down. And then we're going from negative to positive, that's concave up. And so this is for the second derivative. So that tells us, because we have no max or min at 0, and we do have a change in concavity, that means we have a point of inflection at 0, 0. And we also have a change in concavity at 4, negative 256. So that's not showing up as a local max or min, but it is showing up as a point of inflection. Now, the last step in order to graph this is to get a visual of our intercepts. And so for our intercepts, if we want to do y-intercepts first, we're subbing in a value of 0, or again, you could look at your constant. So the original function is y equals x to the fourth minus 8x cubed. There's a constant of 0, so we have a y-intercept of 0. Again, you could sub those in, but we have a y-intercept at 0, 0. And for our x-intercept, we could factor. That gives us x cubed times x minus 8. So we have x-intercepts at 0 and 8. So using all of that information, let's take a look at what this graph would look like. Just setting up the grid here. All right, so let's label some points here and sketch what this might look like. All right, so we know that we have an intercept here at 0, 0. We know that we have an important point at, actually, I'm just going to shift this up a little bit. Because most of the graph is falling below 0. All right, so we have a critical point here at 0, 0. And we know that our highest intercept is at 8. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. So that's an important point there. And I'm going to go down by hundreds here. So 100, 2, 3, 4, negative 500 right here. Okay. So looking at our points, we have a local minimum at 6, negative 432. So here's 6, negative 432. 1, 2, 3, 4, happening right about there. So that's a local minimum. So we know the graph is curving somehow there. And we know we're crossing here. And then we have 2 points of inflection. We have a point of inflection here at 0, and we have a point of inflection at 4, negative 256. So there's 4, negative 100, 200, so 256 would be about here. So taking a look at the graph, doing a real quick rough sketch, we're coming down here. There's a point of inflection at 0, 0. There's a point of inflection down here. The graph is going to curve up, and it crosses there. So it kind of changes direction a little bit here, changes direction a little bit here. Probably should have leveled that off a little bit more. Changes there, and that would be a quick sketch of our graph. All right, guys, so we've covered all of the tools that we need to start curve sketching. Tomorrow we're going to be looking at our last lesson, and this is where we take everything and put it all together. I'm going to give you a function, and you're going to graph it. This is the beauty of curve sketching. See you soon.